and welcome back to linear algebra. Let's jump into Anki. One flashcard. What is the entry in row I and column J of the transpose of A if A equals A sub ij, A sub ji? Easy. So, I'm going to grade what I did yesterday, and then I'll be back to recall how it went in a second. All right, so I got the 2 proofs from yesterday correct, as well as the 3 true and false. So we're going to continue into 1.5, which is elementary matrices and an algorithm for finding the inverse of a matrix, method for finding the inverse of a matrix. Yesterday we touched on the 3 elementary row operations and the 3 elementary row operations that basically undo the 3 elementary row operations that are still all elementary row operations. So that's a mouthful of elementary row operations, but we're going to continue from there, and I'll be back to explain and recall what I learned after I do. All right, ready? Elementary matrices. These are essentially an identity matrix that has had one elementary row operation performed on it. That's an elementary matrix. Every elementary matrix is invertible, and the inverse of every elementary row, every elementary matrix is also an elementary matrix. Well, how is this possible? Because we talked about inverse operations. We were talking about that yesterday as well. Remember, you have an elementary row operation, and there's exactly one elementary row operation that undoes that elementary row operation. So that plus the idea that we learned that if you take an elementary row operation, you multiply it with a matrix, whatever the row operation that was done on the elementary row operation or on the identity matrix in order to become an elementary row operation, elementary matrix, that's the product of that elementary matrix and the matrix will be equal to or equivalent to if you perform that same elementary row operation on the matrix itself. So with that in mind, and with the inverse operations in mind, it's proven that every elementary matrix is invertible, and every inverse of an elementary matrix is an elementary matrix itself. Okay, so we finished that section on elementary matrices. We also learned a term called row equivalence. Row equivalent. 2 matrices are row equivalent if you can get one matrix from another and vice versa via a sequence of elementary row operations. All right, so that's it for today. Tomorrow we're going to start on the next section, which is called equivalence theorem. And that's just a really short section, and then it's a method for inverting matrices, and then that's it for that reading. I don't know what's different, but this section feels a lot easier than previous sections. Maybe I'm just starting to get it better. You know, I've got a decent foundation of terms and algorithms and proofs, and also I'm just more I understand more of what is actually going on. Like, what are we doing? We're talking about matrices essentially in this whole chapter. We're just talking about matrices and their properties as mathematical objects, as well as a little bit of linear systems, but we haven't really touched on linear systems in a while. It's been just straight up matrices for a while. So this is the sections look shorter and shorter. They only look like less than 10 pages each one. How long is this chapter on matrices and linear systems? It is 117 pages, so we're just about halfway through that. So that's it for today. Talk to you tomorrow. See ya.